Hey there, college algebra. This week we are looking at things like slope and slope-intercept and the properties of exponents. And before we really get into it, I just wanted to make a comment, something that I've been thinking about this past week. Um, there's this guy, there's a psychoanalyst named Jordan Peterson. He made this comment in his studies that humans always seem to operate in this nature of on one hand we always have one foot firmly planted into chaos. We're always trying to fix things and fight fires and change the world, and we were always in one foot in chaos. If we put 2 feet into chaos, we're going to be destroyed because we can't handle all of that. There's no way to ground ourselves. And then he says, but we also tend to a good life, a life that's most meaningful and fulfilling for people, is also one that has one foot firmly planted in order. So you got one foot in chaos, one foot in order, one foot firmly planted in security and goodness and fulfillment. That says, things are the way they're meant to be. And he says our goal then is to, as humans, what we do is we try to stick with one foot in order, not 2 feet in order, so that we're like just bored out of our minds and we go stagnant. That's a terrible life. But we go one foot in order and then one foot into the great beyond, into the chaos, and we're always trying to tame the chaos and making order. And I'm gonna get to math in a second, but when I was thinking about that, I was thinking about how that seems to be exactly the way it is with God and how God made the world. Because think about it, when God made the world, it started off formless and void. And many theologians often think that that's not just, there was nothing there. Some people think that meant there was chaos. There's chaos all around. Um, and God took that and he spoke and he made order. He made order out of chaos. He took this chaos and he made something good out of it. And something very, very systematic and not just like orderly, but like beautiful. And then he made us and he says, go and and then what's the first thing he tells us? He says, go, name the animals and subdue the earth. And that's exactly what we did. We named animals and we created order. We said we ordered the animals. Here are the animals, here's their names. And we ruled over the earth. We took over the earth into control, and we said we filled the earth and subdued it. We put it under control. We put it under order. We kept going to that chaos. And it seems like, that God in his goodness kind of made us in a way that we really only live life best when we focus on that chaos and order. and and then I look at math and I see this, I see all these symbols and things and all this stuff, and at first it looks like it, I mean, sometimes it looks like just pure chaos, but when you really look down to it, if we really had the time to look really deeply into every single little bit and to look at every single little bit, and I want to show you today specifically that it's all just a whole ton of order. And that's really all it is. It's so orderly. And to me that shows me that the beauty of God. This math here is an example of the order that God created in the world. So when I see this math and I see the order and I find that, I see God and his handiwork. And I just think it's so cool. And on the other hand, it makes this other thing. It says that, math is incredibly useful to us. It's extremely useful because even if you never use math ever again, even if you go through this class and you're done and nothing ever happens, your brain is still learning how to take that chaos and bring it into order. Because that's really every math problem, isn't it? It's just weird. You got this problem. You've got a problem, and we need to make it orderly and we need to solve it. And that's what we're doing. And so when we do math problems, we do all these really tough things, we are learning how to tackle tough things and really tackle hard things, how to do hard things and turn the hard things in the world into order, to take them face on and say, I'm going to take this, I'm going to tackle it, and I'm going to do it well, because that's what God has called us to. And so when I see tough math problems, it's to me, I get to see God's handiwork equipping me yet again for whatever lies beyond, training me for whatever is going to happen next. So I don't know. There's so much. I could go on this all day. Like I was just talking to pre-calculus. I know I'm going on a long tangent. I'm sorry. We're gonna get into the math in just a second here. But I really want you to make sure you get this, because in pre-calculus I was telling them, that the more I see math, the more I see the signature of God. Because I've seen that in like theology, for example. When we look at Christ, when we look at Jesus, he's or just the whole nature of everything. When we talk about salvation, we talk about the Bible and our faith in a nutshell. We say, okay, well, you died. Well, you're a person. You've made huge mistakes, and that's really, you offended a holy God, and God found a way to save you, and He offers you a new life. And that's really all it is in a nutshell. It's really all our, like, that's what the story is. What happened, and something so simple, something so profound, something so good and so orderly, and yet now we take that and just everything. It takes so much to unpack that. Something so simple, anyone can understand it. But now look at this. Like I've got shelves and shelves and shelves all over here, just trying to unpack and understand what does that even mean. The fact that God would do that for us, and the fact that this happened. How does that change our lives? And so the more we explore this simple idea, this simple concept, the more we see the complexity and the beauty and the intricacy of all this means and what's going on. That's the same thing with Genesis, like Genesis 3, and with the fall, and with Cain and Abel. These are just passages, simple, just stories. But God shows up, and he and and through it we see the full complexity and beauty of God. You could just read the story and be done with it, and you can get something good out of it, and there's a moral in it. But we've noticed the more you study those passages, the more you see incredible depths of wisdom and knowledge. And you could study those passages for your whole life and keep getting stuff out of it. At least that's what I've been noticing. Years and years and years I can study these passages, and I'm still getting so much out of them. So anyway, the signature of God in my mind is that something that's really simple, but but as the more you study the simple thing, the more you see the really beautiful complexity behind it. And that's exactly what math is. Now that's what's so cool. Math is exactly that. It starts off as simply just 1 plus 1 plus 1 plus 1 plus 1, or just adding a bunch of numbers together. And that's something we all do. It's really simple. Anyone can get that. But the more you study math, once you understand addition, then you say, oh, what if we plus a bunch of numbers really fast? That's multiplication. What if we add groups of numbers together a certain number of times? That's multiplication. And then what do you say? What if we multiply different groups of numbers multiple times? That's exponents. What if we do the opposite of exponents? Or what if we do the opposite of multiplication? That's division. What if the opposite of addition? That's subtraction. What if we do group exponents together? Well, that's powers. And then we keep going and we get to these things like factorials and integrals and all that stuff, but it's all really just really fancy addition. This really beautiful, orderly thing of addition, and from that comes stuff like from something that's so simple and beautiful like addition, we get things like e to the I pi equals 1, which is its own really crazy, beautiful, immense thing. And so from a beautiful thing comes another beautiful thing. From the beauty of God and what God's done on the cross becomes this beautiful love relationship with Him. Beauty begets beauty, and God created you a beautiful being, and He anticipates you to make beautiful things in front of Him. And oh man, I hope you do. I'm really excited to see how you do when you graduate college, and even now, the kind of beautiful things you're going to be making. You were created to make beautiful things because you are a beautiful thing, and that's why I love teaching you all. So, oh man, I'm getting on huge tangents. I'm sorry. Let's get in and let's get into the actual math. Let's look at some of this order that's been created, some of this simplicity, that if we understand the simplicity, it creates the complexity. And I hope when we actually go through these things, you could just learn the rules, sure, and you can know the rules, and the rules are fine. But once you understand, if you understand the ideas, then you don't need the rules. You don't need to memorize anything. You can just understand the ideas and make the math on your own. Once it's like the law, when you study the law, you're just doing. You gotta learn the rules and do the rules and always do these rules, and you always have these rules in your head, and it's overbearing and it's overwhelming. That's the law. But when you get But when you get the heart that Christ gives you, once you get the understanding, the intuition, the law is written on your heart, so you can just do whatever you want because you know you're going to be following the law of God. Um, Same thing here. When we look at these math problems, we can learn the rules and be overwhelmed with rules. But if we get the intuition, if we get the heart of what's going on here, if we understand the numbers and the beauty of the numbers, and the beauty of what's happening, then from that we can just do whatever we want, and we'll have as much freedom to mess with the problem however we like to solve it. And and I think that's to me, I think that's the more enjoyable way to go. But I am not here I guess I've already preached to you. I'm not here to preach to you. We're here I'm here to give you a couple of different ways of looking at these problems, so that you can be ready for them for whatever God has you called you to, and for the here and now, just so that you can do it well, so you can do these problems well. Okay, all that side. Sorry, let's actually get into it. Here's what we're learning. We're learning we're learning a slope, how to find the slope-intercept, and the properties of exponents. I'm going to start with the properties of exponents because that's in my head the most intuitive, and things can flow from that. So here's the properties of exponents. We'll start with number one. This is number one, and this is the first major main idea. If you get this main idea, you can get the rest of exponents, and that exponents just naturally follows. Is that a times a times a is a cubed, or the idea that if you multiply one a by another a, when we say a cubed, when we say a to some power, in this case the third power, a to the 3, a to the third power, we're just saying we have three a's that are being multiplied together. That's all we're saying. And if we can understand that, if you can understand that that's all that's happening there, the rest can just kind of flow naturally from it. And that comes if you really get that, if you really get that idea and really let that sink into you, then the rest just comes naturally. So if we have a to the 3, that's let's go down. Yeah, a cubed, that's a times a times a, right? And then if we went to a squared, that's 1 less a. We've seen this before. I've kind of written this up a few times. But I want to just make sure that you have a permanent record of this as well. The link to this notebook is in RenWeb. Feel free to go check it out and all that. A times a times a is, I think it'll be in the description too. A times a is a cubed. If you go one level down, you go to a squared, you get just a times a. Or in other words, it's more like you're just dividing a times a times a by a. Here's what I mean. Where it's like, sorry. Looks like my undo button isn't working so well today. If I divide a by a by a times a by a, well then one of the a's cancel out and we get a. So it's kind of like to go from one step down, we divide by a. If I divide by a again, we cancel one a out and we get a. A is a to the first. If I divide that by a, then we get 1, or a to the 0 power. Because a divided by a is just any number divided by itself is just 1. This is just 1. Okay, and then if we keep going down, so that's the first thing to know. That's the first thing to notice. That 1 is just a to 0, or anything to the 0, anything to 0 at all. It could be 3 to the 0, 7 to the 0, 2i pi 7 3 to the 0. Anything to the 0 is always going to be 1. We could talk about 0 to the 0, but that's a different topic altogether. So 1 equals 8. I'd love to talk about that one, but we just don't have time. I'm so sorry. Let me know if you'd like me to make a video on that one. I'd love to. I could reference a good one. So 1 equals a to the 0, and if we were to keep going, so anything to 0 power is 1, but if we were to keep going, we could divide by a again. If we divided this by a, we get, 1 over a. And that'd be a to the minus 1. Remember on the right side, we're counting down by 1, so we just subtracted 1 over here, subtract 1, subtract 1, subtract 1. If we subtract 1 again, we get minus 1. If we subtract 1 again, we'll get minus 2. And how do we get minus 2? We'll just divide this whole thing by a again. We could divide by a again. And that'll give us 1 over a times a. Or 1, and then if we keep going again, we go 1 over a times a times a, and that's a cubed. A to the negative 3. This should be negative 3. Okay. So that's all of those things. But the real things I want you to make sure that you really understand in that is that what is a to the 0 is 1. Anything to the 0 power is 1, and anything to the negative power, excuse me, oh my goodness. Let's try to get back in a reasonable place. Okay, anything to a negative power, to find the negative power, you kind of just flip it. So let's see, a to the 1 over a is just 1 over a to the first. If I do 1 over a times a, this is 1 over a squared. And 1 over a times a, that's 1 over a cubed. So if I do 1 over a to the negative 1 is just 1 over a. A to the negative 2 is 1 over a squared. A to the negative 3 is 1 over a cubed. In order to get from one to the next, if you want to get rid of the negative in any exponent, all we got to do is find what's called the reciprocal, bring it down below a fraction line, or if it's already below the fraction line, you bring it above the fraction line, and then just make it positive. So if I want to go from, 1 over a cubed is a to the negative cubed, because I can just take this a cubed, bring it up, and make it negative. Or if I want to do the opposite, I could say, 1 over, say a to the negative 7, I'll bring that up, and that becomes a to the 7th. Or maybe I want to do this. I want to say a to the negative 4th. That becomes a, sorry, not an a, that becomes 1 over a to the 4th. I hope it's making sense here. We just flip it. We can flip it and then change the exponent. We can change the exponent from positive negative or negative positive. This is possible in any fraction. If we had 2a to the 4th over 7, it could become 2 over 7a to the negative 4. So that's all we're doing here. We can just flip it and change that sign. Okay. So, and that's the intuition. That's the intuition behind all that is happening. So just by understanding a times a equals a cubed, just from that, we were able to discover what a to the 0 power is and what a to the negative powers are, and how to flip things to do that. We can also go a different direction too. We can go to what I call stage 2 of this idea of multiplying a's together. But what happens if we want to take a squared, which is a times a, and multiply that by a cubed, which is a times a times a? Well, if you multiply a times a with a times a times a, that gives you, let's see, a times a times a times a times a. That gives you just 5 a's. So if you have 5 a's, that's just a to the 2 plus 3, or a to the 5th. So, and 5 is just, well, 5 is 2 plus 3. It is a to 2 plus 3, or 5. We're just combining them together. The 2 and the 3, we're combining them together, so we get a to the 5th. In other words, when you want to multiply, what that tells us is when you want to multiply, when you're multiplying two exponents, you add them together. You can just add the exponents together, and that'll get you the answer. Keep in mind though, let's before we get too far with this, let's keep in mind, let's make a caveat here, because if we had something else, let's explore something else. If I had just on the side, if I had a squared times b cubed, that would do something a little bit different, because that would be a times a times a. So not a times, that's just 2 a's. That'd be 2 a's. There we go. And then on the right side, we'd multiply that with b times b times b. And so what we get is, let's see, that'd be a times b times b times b. Can you see how that's different from a times a times a times a times a? Because no longer, we have just like 5 a's lumped together. And so we could say that's a to the 5th. We could say this is a to the 5th down here. But we can't say that for this one, because we don't have 5 a's. We have 2 a's and 3 b's. So we're kind of just stuck with saying we've got 2 a's and 3 b's. And so we really can't condense it down anymore. What this tells us here is that that's something that's really helpful. That tells us that if they have to be the same base, they have to be the same number on the bottom for us to combine them. Otherwise, they're just not combinable. It just won't work. Okay, so same base, that's important. Same base is important. Or actually needed. Let's say needed. That's better. Okay, so that's the idea. What happens if we take, let's say, a to the 5th, which we know is a times a times a times a times a, and then we divide that by a to the 3rd. That's a, which is a times a times a. Well, if we take a times a times a times a times a, all those 5 a's, and we divide that by a times a times a, let's kind of rewrite this. Well, we'll be fine. If we divide that by a times a times a, let's make this as a clear line. Divide. Well, 5a's divided by 3a's. We can just do some canceling here, right? We could just cancel out this a and that a. We can cancel these a's. We can cancel these a's. That gives us, well, that just gives us 2a's left. So we just canceled out 3a's. So if there's a 3 at the bottom, if there's an exponent on the bottom, that means we're going to cancel out 3's. Instead of add 3a's into the mix, we're going to cancel out 3a's from the mix. So that gives us a to the 5 minus the 3 we canceled out. So that would give us a times a. That's not, it should be 2, that should be 3. So 5 minus the 3 we canceled out, or a times a. In other words, what we can say to kind of generalize what we just did here is we can say that when we divide like this, what that means is that when we divide like this, that means we're just subtracting the exponents. We can just take 5 minus 3, as that's kind of shorthand, and that'll tell us what the answer is. Or, because 5 minus 3 is 2. So the answer to this one would be a squared. Cool. Cool. So just from that, again, just from a times a times a equals a cubed, we have discovered all these things just by using that one rule and learning all the different intricacies of that one rule, along with the very basic arithmetic that we're used to. Okay, that's stage 2. What if we went one stage deeper? Let's say, for example, we wanted to take a to the third, a cubed is another way of putting that, and we wanted to square it. We wanted to bring it to the second power. Well, what does that do to us? Well, we know that when we square anything, let's go back to the original definition. We said that if we got a cubed, oops, that was an eraser. If we have an a cubed, that means we just have 3 copies of a multiplied together, a times a times a. So if we've got a cubed squared, that means we've got 2 copies, or 2 a cubes put together. Two copies of whatever's in this parentheses. We've got 2 copies of that, and we're multiplying those together. So that means we've got an a cubed times an a cubed multiplied together. We're multiplying a cubed and a cubed. That's what that's telling us. So a cubed squared is saying a cubed a cubed. And, well, what is a cubed a cubed? Well, a cubed is, let's see, we can do that. We can do that because we know stage 2. Stage 2 tells us a squared times a cubed. Anything that, when you get multiplying exponents together, you can just add the exponents. So we can just add these exponents. We can say it's a 3 plus 3. Or in other words, you can say, if you remember, like, how if we say, like, 3 plus 3 plus 3 equals 3 times 3. Yeah, that's a bad definition. That's a bad example. Let's say we said 4 plus 4 is 3 times 4. Similarly to that, if we have 2 3's we're adding together, we can say that's 2 times 3. We got 2 times 3. So what we've got is a to 2 times 3. Or in other words, a to the 6th. So if we've got a to the 3 squared, what we actually end up doing is we multiply. We got a to the 3, oops, no, please no. If we have a to the 3, a cubed squared, a to the 3 to the 2, that means we're going to end up with a to the 2 times 3. That's the same thing. We can multiply those 2 numbers together. So when you're raising a power, when you're raising an exponent to another exponent, we will just multiply. That's what that's saying. So cool. So just from learning what we learned from stage 2, we can learn something even deeper in stage 3. We've learned that a power to a power is just something we can multiply. And again, we learned stage 2 from stage 1, just that one concept that a times a times a is a to the cube. That's all that means. So that's really, really cool. So that's the essence of what the exponent rules are. That's just these basic ideas. These are the exponent rules. If you can get these down, you'll have exponents. We're going to do some problems to explain how to do that well. Okay, so that's that. Now let's switch over to the other side and look at finding slope and slope-intercept. Okay, so we've got, let's make some definitions first of just what do we mean by slope-intercept. Well, when we say slope-intercept form, what we're actually saying is we're just saying a really special way of writing an equation. We are saying we are saying specifically and exactly y equals mx plus b. That's what we're trying to write when we say slope-intercept form. Y equals mx plus b. It's confusing, and I don't like the way that mathematicians wrote this, because it seems really confusing to me. That's why they chose the letters that they chose. They do have reason behind it. I just don't think they're good reasons. So, but this is the what they've decided is that m is going to be considered slope. Whenever you see the letter m, think slope. Whenever you see the letter b, think y-intercept. Again, there's no really easy way to remember that other than just saying, hey, b is y-intercept, m is slope. We call it slope-intercept form because we go with slope, and then there's the intercept. That's how I initially helped me remember it. Which one was which? The first one's slope, and the second one's the intercept because it's called slope-intercept form. Cool. So that's slope-intercept form. That's what it is. We're gonna see how to get it pretty soon, how to find it from a bunch of different ways. What is slope? Well, slope is just rise over run. If you remember from a graph, we're gonna find a graph right here. It'd be the number of, if it's rise over run. It's the amount that you rise. Let's see the amount you rise. In this case, we fall a certain number for every time over the amount you run to get to another point. So you choose 2 points. Oops. Yeah, we choose 2 points, and then let's say I chose this point, and let's say that point. It's literally just the amount you rise. The amount you rise. In this case, we rise in -4, so that's a kind of a bad example. I'm sorry. And then how much you run to. So that'd be a negative. You put the -4 over 2. Another way of doing it is something fancy called y2 minus y1 over x2 minus x1. And what that means, what that means is that, and that's really used for points. If you've got some points, you can use the exact same thing. And again, I don't have too much time to go into why. This is just kind of the rule I'm going to give you. But I'd love to go into why. If you have questions as to why, I'd love to tell you. The reason this is something we use for points. If you got 2 points, let's say x1 y1 and x2 y2, because you got point number 1 and point number 2, you can rewrite them. You can put these numbers, let's say it was 2, 3, and 4, and 5. You can put those numbers into this formula, y2, subtract y2 from y1, 5 minus 3, and subtract x2 from x1, 4 from 2, and that'll get you the slope. That'll actually tell you what the slope is. A way of thinking of slope intuitively is just, how heavy, how steep is the line. If you're a runner, the example I keep using all the time is, if you're a runner, how heavy is this hill? Is it flat ground? Is it 0? Is it like a 45-degree angle? Is it a slope of 1? Is that the normal slope? Is it really high? Is it like a slope of 2? So every time you run like 1 foot forward, you're going 2 feet up. What's going on? And so that's kind of what the slope is trying to ask of you. Okay, that is slope. Now, if you want to find the slope, well, so we've made our definitions now. Now we're going to actually use them. If you want to find the slope-intercept equation of a particular graph, then you just pick 2 points, like we've done here. And the first thing is you find that rise over run. You find the slope. So in this case, this would be -4 over 2. So that's the slope. That equals our m. So that's step 1. Step 2 is to find the y-intercept, the place where it intercepts with the y-axis. So that'd be, in this case, this would be -4. So this intercepts at, this is intercept at -4. This intercepts at 4. So on the place on the y-axis, this is 1, this is 2, this is 3, this is 4. The place it intercepts with the y-axis is 4. So on the y-axis, it hits 4. So that means our y-intercept is 4. So 4 equals our y-intercept, which is, again, it's just the letter b. So third step, all you gotta do is plug those numbers in. Our equation is y equals mx plus b. So we're going to plug in y equals -4 over 2 x plus 4. It's good to simplify, as always. So -4 over 2, that, as you may be able to figure out, is just -2. -4 divided by 2 is 2. So y equals 2x plus 4. And that's the equation of this line. I mean, I'd love to go into more explanation of what even is a line and why is this equation so important? Why is this equation attached to the line? But that's for another time. We get the same thing with numbers as well. With numbers, if we had, let's say we plug those numbers in. Let's say this is the point. That was the point 0, 4, and this is the point. Let's say that's 2, 0. That's what that is. Yep. And so we can plug those points in. Let's say we had the points 0, 4 and 2, 0. Okay. So y2 minus y1, that'd be 0 minus 4. y2 minus y1. And then x2 would be 2. And then x1 would be 0. So you just plugged it in. So the slope equals -4 over, what? 2 minus 0 is 2, which is our slope again. And again, you might want to just see, look at this and say, oh, -4 over 2, that's just -2. That's probably a good idea. So -2 equals our slope. Okay. Let's just let's go ahead and clean it up and make sure that that's clean. That's clear. Okay, now we find the y-intercept. Finding the y-intercept is a little bit different here. We'll actually, the first thing to do is to write that equation again. Y equals mx plus b. And we're going to plug in the slope into the y-intercept equation. So we'll plug the -2 in. We'll get y equals -2x plus b. But we're still doing the same thing. We're just doing the same thing. The first step was to find the slope. Second step is to find the y-intercept. And the third thing is just plug those two into the equation. Like in the first one, like in graphs, find the slope, find the y-intercept, plug it in. So we're in the step 2. We're trying to find that y-intercept. To find that y-intercept, we're going to plug in we're actually going to plug in temporarily the slope into the equation, and we'll plug in any other point we want. Let's say we plug in the point 0, 4. It really doesn't matter. We'll plug in 0, 4. So 0 is our x and 4 is our y. So we get 4 equals -2 times 0 plus b. So -2 times 0 is 0. So 4 equals b. This cancels out. So 4 is our y-intercept. That's actually not the answer. Let's forego on that. And then you just plug that into the equation. So again, you do y equals mx plus b. We'll plug in the m and the b. So we get y equals -2x plus 4. And that is our answer. Okay. And that's really all there is to this lesson. All the rest of this lesson, all the rest I'm going to talk about from here on out is I'm just going to go through a bunch of problems with you. So that if you're struggling with a particular problem, with a particular idea, just come back here and I can help you through a particular problem through this video lesson. If you'd like to just go to the problems now and just work on them and get them all done, great, perfect. But if you'd like to work through the problems with me, with my guidance, then these next few problems will be there to help you work through each little problem, or each separate kind of problem, so you can get a kind of an idea of how to apply these concepts, especially in certain weird situations. Okay, let's jump into the first problem then, so we can kind of get an idea of how to do this, how to apply this. So it says, find the slope of the line. Well, we've got this graph, and we want to use the rules for the graph. Remember our rules. Our rules are first, find the slope, then find the y-intercept, and then plug that into the equation. So we need to find the slope, find the rise of a run. So what's the rise of a run? Well, the rise of a run, let's see. We go from this point down here, all the way up to this other point up here. Let's see, what's that point at the, well, let's see, what is it? How do we, when we rise, how far do we rise? We rise, let's see, we rise of 1. To get from the first point to the second point, we rise of 1. And we run how far? We run 3. Okay, so for our first step, we're trying to find the rise of a run. And the rise is 1, the run is 3. So that is our slope. Perfect, we're done with that. Second step is to find the place where it intercepts with the y-axis. We can kind of guesstimate it at first, and you can kind of see a little bit of where it's landing. It's landing right around here. It crosses that y-axis right there, and you can kind of guess, if the slope is 1/3, well, at first you can kind of guess and just kind of see. It looks like it's about 1/3. And then intuition would be right, because if we are, the idea of slope, what slope is doing every single time, is that every single time we move forward 1 unit, we're going to go up the slope. Here's what I mean by this. If I started here, let's say this is the y value of 1. Up here, we're going to rise this slope. We're running every single time we go over 1 unit, we're going to rise the slope. So we'll go to 1 1/3. This is 1 2/3, and this is 2. If I was to go on further, then to the next unit, it'd be 2 1/3, 2 2/3, and then 3, and so on. So every single time I move forward 1, I'm moving up the slope. Because that's the kind of intensity of that's what the slope means. It's the kind of intensity of the hill. How fast it's going up for every time we move forward a foot. How many feet are we going up? And since we're gonna go 1/3 feet, so that's what we'll do. So if we start here, this is the x-axis. It says this is ground zero, and so if we go over here, this is gonna be 1/3. So we can be sure this is right here on the graph. This is 1/3. That's 1/3. Okay, equals our y-intercept. And so our equation would be y equals mx plus b. And so our equation would be y equals, let's see, that's 1/3 x. Let's see, I'll plug in our m. That's our plug in this m. That goes in there. 1/3 x plus 1/3 plus that b. And that's the answer. I feel like I was a little bit unclear with 2. I just want to make sure that I'm not just kind of jumping through hoops here. The idea of number 2, what we're doing with the slope is if you wanted to go through it a different way, you could, if you're struggling with this idea of going 1/3 every single time, another route is just going the equation route, which we'll look at in just a few minutes with a few problems down. You could just say, y equals mx plus b, and you could say, let's plug in 1/3, so y equals 1/3 x plus b. Then you could have plugged in one of these 2 points. Let's say this point on the left is, let's say the point on the far left, that is -4, -1. You could plug that in and then find the y-intercept. So you could plug in, negative, x value, the y value is -1, so -1 equals 1/3 times -4 plus b, and then we solve for b, so that equals, -1 equals -4/3 plus b. We add 4/3 to both sides, and I hope I'm not belaboring the point. But when we solve this, we will get, let's see, -1 plus 4/3 is 1/3, and then these 4/3 cancel out, so that gives us just 1/3 equals b. So the idea is you can still do this with an equation if you wanted to use the equation route. But if you can just kind of see it graphically, and graphing it helps you better, that works just fine as well. Just make sure you're guessing. With the graph, when you look at it, you can look at and make an estimation with where it is if it's not on one of the actual tick marks. But then after that, you want to check by looking at the slope and seeing, does the slope line up? If I keep counting the slope high, if I keep going up the value of the slope every single time when I move forward, will I get to where I estimated? And that's kind of the idea of what we're trying to do here. Okay, I hope I wasn't too confusing. If you're still confused, just come ask me. I'm here to help. Cool. The next question. Write the equation of the line in slope-intercept form. Oh, wait, oops. This one's just find the slope. If the slope was 1/3, that's what that is. Slope is 1/3. Oops, that was that. We've kind of found we found the slope, and we found the y-intercept. So I guess we'll do it again. I clearly didn't read the directions. You should go storm me in the comments about how I'm such a terrible teacher. Okay, this one actually doesn't give us points, so we kind of have to find our own points here. One of them is right up here. This is at 4, and then at the bottom we've got one down here. These seem to be the places where it actually crosses the x-axis, or crosses like actual corners of the grid. The places you're looking for are places where it actually like touches those corners of the grid. So like corners like here and here and here. When it touches these corners, that's a solid point. If you can find those, those are the best. And so you can see it doesn't really touch a corner anywhere except for right there at that 4, the y-intercept at 4, and then right down at the bottom, right above the 5 on x. So those are the places that would actually touch the corners. Those are the places that we actually want to use. Okay, so if we want to find, we're going to start with step 1. Again, so we find the slope, which is the rise over the run. And let's see, how far do we rise? In order to get from the first point to the second point, we have to rise. Let's see, we can't go up anything. We have to actually go up a negative amount. We're going up a -3, and then we have to go across. Let's see, that's 5. We have to go across 5, and so our rise of run in this case is -3 over 5, or -3/5. So that is our slope. That's our slope, -3/5. There's no way to reduce that number. That number is as far as it can go. Okay, so then now we've got the slope. Let's find the y-intercept. The y-intercept is placed at intercepts of the x-axis, sorry, not x-axis, the y-axis. And conveniently, to our great convenience, the point that crosses the y-axis in this case just so happens to be a point that's in a corner, but a point that we can just label. This is the point. This is the point 0, 4. Because it hits one of those corner points, it hits straight in the corner of the grid, in one of these grid corners. We can actually give it a solid point number. We can say this is the point 0, 4. So we can just say the y-intercept, the place it intercepts the y-axis is at this 4 tick mark. It's right up here at the 4. So 4 equals our y-intercept. Cool. And finally, third, we're going to put them together. I guess I'll use a third color since use a different color for 2. Let's use yellow. 3. So thirdly, we want to put them into the equation. Our equation is y equals mx plus b. And let's see. Our first one is, our slope is -3/5. So we get -3/5 x plus, 4 is b. So we put in 4. And this, and that's it. That's our answer. Now, a quick tip when you're writing equations. I probably should have said this at the beginning. I'm sorry I didn't. But an equation will always, just about almost always, for our intents and purposes, will pretty much always have y and x as letters. We'll keep y and x as letters, or what we call variables. However, we can't have anything else as letters. For a completed equation, for an equation that works, usually for all the things that we do, we really don't need anything else. We don't want anything else to be letters. We want to get rid of all the letters, but nothing else. So that's really why. That's kind of, maybe if that's more of an intuition as to why we wanted to figure out what M and B are in the first place. We want to figure out these letters because if we want to finish the equation, we've got to replace those letters with numbers. Because who likes letters in equations anyway? They're just causing problems. If we can get rid of them, then all the better for us. So that's what we're trying to do here. We're trying to get rid of M and B, so we can make an equation that has just X and Y as our letters. Okay, I'm kind of getting off track here. Let's move on to the next problem. All right, write the slope-intercept form of the equation of the line that goes through the given points. Okay, so we've got a line. Let's see the slope-intercept form of the equation of the line. So we're gonna write this. That's the first part. The slope-intercept form of the equation of the line. So we're gonna write the equation of a line. We'll put that in slope-intercept form. Okay, so that's y equals mx plus b. And it goes through the given points, 0, 1, and -2, 3. Okay, so we'll just go through the same points again. So we'll start with the slope. And we're going to say the slope is y2 minus y1 over x2 minus x1. If you think I pulled that out of the air, well, I sort of did, but that's way up in the instructions at the top of the notebook that I got that from. I wish I could explain the reasoning behind it, but I honestly just want to save you time here, so I'm not going to do that quite yet. So in order to find the slope, we're just going to name some points and then figure it out. So let's say this is point number one, the first one. Let's say it's called first one, point number one, and the second one, point number two. And let's label which coordinate is which. Let's see, the first one is the x coordinate, and this one is the y coordinate. This would be the x coordinate, and this is the y coordinate. So let's see, this is the x coordinate of the first point, so it's x1, the y coordinate of the first point, so that's y1. This is the x coordinate of the second point, so it's x2, and the y coordinate of the second point is y2. Okay, cool. So now we know what x1 and y1 are, and x2 and y2 are. The first point, second point, and then we've labeled x and y. And honestly, if you wanted to switch it up and say that, well, I don't want to confuse you, but if all this is boring stuff to you, just know that you can actually switch these points and say 2 becomes 1 and 1 becomes 2. So you could have done x, you could have said 0 is x2 and negative 1 is y2, and then negative 2 is x1 and negative 3 is y1. And that would still work out to be the same answer. But if that's at all confusing, just forget it. Just forget I said anything. So let's jump into this. So let's plug in the numbers. We get negative 3 minus, because that's y2. Y1 is a negative 1. And then we're gonna I put that in parentheses just because I want to keep these minuses in track. I didn't want to I didn't want to have a minus and really get confused. So I just put parentheses to kind of help remind me, hey, there are two minuses here. We're gonna work with them soon. So x2 is negative 2, and x1 subtract 0. So minus x1 is 0. Okay, so we're gonna solve that. So 3 minus a negative 1 minus a negative, that becomes a plus. So negative 3 plus 1. Oh gosh, so I've got a debt of $3, and then I owe someone $3, and I give them $1. So how much money do I have? Well, I don't have any money. I still owe $2. So I'll say that's negative 3 minus plus 1 is negative 2. And then negative $2, I owe someone $2, and then so nothing happens. So I still have a debt of $2. So negative 2. Okay. Oh, great. So we get that equals negative 2 divided by negative 2. Negative 2 divided by negative 2, that would be anything divided by itself. Anything divided by itself anywhere, at any time. That's always going to be 1. That equals 1. So our slope is 1. 1 is our slope. That's our slope. And we use m to define slope. Okay, great. Now we're going to find the y-intercept. y2 is the y-intercept. And to do that, we're just going to plug in these numbers. We're going to write that equation, that y equals mx plus b. And we're going to temporarily, just for the sake of this step, not really for full scale, we're just going to, just for the sake of step, we're going to plug in the slope and then a point and see if we can find out what b is. Okay, so plug in a point. Plug in the slope, excuse me. So m is 1, our slope is 1, so we get y equals 1x plus b, and then 1x plus b. I'll plug in at any point. Let's just plug in the first point, because why not? So we'll plug in, negative 1 equals 1 times 0 plus b. And again, if you understand the logic of this, you can do whatever you want. I mean, you can go a completely different route than I'm going. But this is, if you're really struggling, this is a solid way forward. But it's your problem. You can do it however you can do it how you want, as long as you're not breaking any fundamental rules of math. You can do whatever the heck you want to solve these problems. I don't care. And the problem doesn't care. It's free. It's a free problem. It's not just like it's trying to constrict your throat or anything. You can do whatever you want with it. So I feel like I'm Bob Ross now. 1 times 0 is 0 plus b. So let's see, negative 1 equals b. Excellent. So our y-intercept is b. Great. So 1 is our m. Y-intercept is negative 1. So we'll just write our answer, 3. So our answer is, we'll write the equation and we'll plug in the slope and the y-intercept. The slope is 1. So y equals 1x plus a negative 1. And we'll reduce that down a little bit because it's good to have a reduced answer. So y equals, let's see, 1 times x, 1 times anything is itself, so we'll just say x. And then plus a negative 1. If you add a negative 1, that you're just going to subtract 1. So that's a positive and negative becomes a negative. So x minus 1. And that is our answer. Y equals x minus 1. Great. Okay, let's move on. Now the next set of problems are all just using the powers of exponents like we've been talking about before at the very beginning of this. And so I'm going to kind of move through these rather quickly. I'm going to move through them, not really quickly, but I'm going to move through them in succession so you can kind of get the idea of what we want to do here. Okay, it says, because they all have the same rules, it says simplify, and your answer should only have positive exponents. Simplify with positive exponents. Okay, we can do that. So simplify. What can we simplify here in this first problem? Well, we've got y to the 0. So the problem is 4 times x to the negative 2 times y to the 0. Now, what can we simplify here? Well, so remember our rules. Way back up at the top, we remembered that, let's see, what can we do up here? We know that anything to, let's see, a cubed is just a times a. We also realize that anything to the 0 power is 1. And if you have a negative 1 power, you can flip it and make the sign positive, or make the power positive. Okay, so maybe those will help us. We don't have any exponents being multiplied together. We do have exponents multiplied together, but they're different. They're different bases, so we can't really just multiply them together like normal. So stage 2 would tell us to multiply the x and the y together, but we can't multiply the x and y together because they're different bases. They're not the same base. But what we can do is remember that y to 0, that's something to the 0 power. Anything to the 0 power is always going to be 1. So we'll start with that. So we get 4x to the negative 2 times 1. Great. So that's a great way to simplify it. We've just gotten rid of a whole variable. So that's really helpful for us. The next thing we can do is we can say that, okay, x to the negative 2, the negative 2 power is, if you want to have a positive exponent, that's what it says up here, we want to have a positive exponent, we can do that by flipping it, by putting it over the fraction, putting it underneath the fraction, and then changing the sign. So we can say 4 times 1 over x. Instead of putting a negative 2, we'll put a positive 2. That's the idea. So again, all I did is I kind of here's what I kind of did. I took a 4 times 1 times x, it's negative 2, and I put it over a 1, because you can divide by 1 at any time, and it'll still be the same thing. I took the x, and I just kind of brought it all the way down to the bottom, and then I made it positive. So I brought the x and made it positive, and I brought it down. That's kind of all I did here. Okay. So you got 4 times 1 over x to 2. Well, 4 times 1, we know what that is. That's just 4. So we get 4 over x squared. And that looks pretty simple to me. I think there's nothing else we can do there. That's as simple as it gets. So that's the answer to that one. So great. This is the next one. The next one says 4mn to the negative 4 times m to the third times n squared. Interesting stuff we've got here. Well, let's first try to group these together so you can kind of see what it's doing. A lot of these m's and n's, it looks confusing. So let's say that's an m, that's an m, that's an n, and that's an n. Okay, so I'm trying to make sure my dyslexia doesn't like kill me or anything. I don't know if I have real dyslexia, but it feels like it sometimes. So we got 4 times m cubed times n to the negative 4 times n squared. And all I did there is I realized that, well, between a 4 and an m, there's always, if a bunch of numbers or letters are mashed together, there's always imaginary multiplication signs between them. So I kind of first realized that there's always these imaginary multiplication signs. And then, on top of that, I can kind of move things back and forth however I wish. I can, if they're all being multiplied together, if everything is being multiplied, I can move this 3 over here, I can move the n over here, and I can just do it however I'd like. And so that's all I did here. Okay. And so I said m times m to the 3. Well, that's m times m times m times m. There's just 3 m's and 1 m. So we can add those exponents. That'd be m to the fourth. So this gives us 4m to the fourth. And then we get times, let's see, n to the negative 4 times n to the 2. We can add those exponents too. That'd be n to the negative 2. Yeah, okay. And now we can do the same thing we did in the last problem. We can say, we got the negative there. We want to get rid of that negative. We got like positive. So we'll go ahead and do that. We'll take the negative and we'll put it over a fraction. We get 4m to the fourth over n squared. And that's it. And again, you could have done this a bunch of different problems. You could have done this a bunch of different ways. You could have gotten this answer a number of different ways. You could have done the n4 to the n4 first. You could have done the first move you could have made was 4m, m cubed n squared, and then put that all under n to the fourth, and then work from there. And then did a property of division and said n squared divided by n to the fourth is n to the 2. So 4m 3 and 2, and then we could have done 4 add the exponents over n squared. There's a bunch of different ways you could have done to solve this problem, and you're free to do whatever you like. As long as you're following the rules of math, you can do whatever you want to solve this problem. And I encourage you just to play around with it, have fun with it. This stuff is built in order. It's chaos that you can build order into, and you can do it however you want, and you can make it beautiful. And so that's kind of what we're doing here. All right. Next problem. 4mn m times n to the negative 4, and all that squared. Remember what we said. We have something. Well, actually, yeah. There's a few things we could do here. Here's the route that I like to go. I remember from algebra, we had those order of operation things where it says like we do PEMDAS, PEMD A. I always get, I think it's an O. Is it AS? And so we do parentheses, exponents, multiplication. I know my handwriting's terrible right now. I'm just trying to get you the idea. Addition, division, addition. I spelled addition wrong. Okay, addition and subtraction. That's what I get from going fast. Okay, and so the first thing I see is like, okay, we got parentheses. I want to deal with parentheses first. How do I take care of parentheses? How do I get rid of these parentheses? Well, what's going on with the parentheses? If it was like a negative m n to the negative 4, I'd want to deal with the negative that's touching the parentheses. This negative is kind of like touching the parentheses. If it was like a 4 m n to the negative 4, I would want to take that 4 and deal with it, because that's what's touching the parentheses. Right now, what's touching the parentheses is a squared, and so I'm going to deal with that squared. So even though it's technically an exponent, I'm going to deal with that first, because I need to do that in order to get rid of those parentheses. And again, honestly, you can do it any way you want. There's a bunch of different ways to go about this, as long as you're not breaking the rules of math. But this is a solid way to do it that's surefire and it's guaranteed, as long as you are following the rules. Okay, so 4mn to the 4 squared, that's the same thing as saying, remember what squared means? It means you have two copies of things multiplied together. So that gives us mn to the negative 4 times mn to the negative 4. So these two things multiplied together. Okay, so I kind of just made like two parentheses here, unfortunately. But I can still do that. I mean, these parentheses are just using multiplication. So these they're just multiplying one thing next to the next thing. And because they're multiplying and everything on the inside is multiplication, everything's just multiplication. So I can actually drop these parentheses. The parentheses don't matter that much. If that doesn't make sense, don't worry about it. Times m times n to the negative 4. We can just have, just think about this. Forget the whole parentheses step then if that didn't make sense. We got m times n to the negative 4 times n to the negative 4. So that all comes together and becomes, let's see, we can rearrange those. So it becomes m times n to the negative 4 times n to the negative 4. Let's see, m's come together to make m squared, and n's come together to become n to the negative 8. And then let's see, if we want to get rid of that negative 8, so we're going to flip it over the fraction and change the sign. So we get m squared over n to the 8th, and that is as far as we can go. Those m's and n's can't combine, so that has to be our answer. Great, good deal. Okay, 4xy divided by 4x to the negative 2, y to the 4th. Okay, there's a good deal going on here. Let's see what we can do to solve this. Let's see, we've got some y's, we've got some x's. We can't combine anything on the top, we can't combine anything on the bottom. They're all just kind of stuck the way they are. So we can kind of try to see if we can pull these together. There's a couple ways of doing this. Let's start by saying let's start by looking at the how about we start with the y's. That sounds like a good idea. Or maybe we could just start let's start by looking at the y's. 4xy over 4x to the negative 2 y to the 4th. I might be missing something really obvious, and if you see something obvious, just do the obvious thing too. So yeah, let's just do that. So y divided by y 4th. We can kind of split this up again because it's all multiplication. If it weren't all multiplication, we'd have a problem. But because it's all multiplication and division, we can just use these rules of multiplication and division here. Again, if we had like 4 plus x times y over 4 times x plus x negative 2 plus y to the 4th, that would be something completely different, and we couldn't use these rules in the same way. But because those would be different terms. But this is all, if you remember what we said last time, a while ago, about terms, this is all technically one giant term. And because it's all one giant term, we can all treat it, the whole thing together, all as one. It's all one giant messy thing. So we can use the rules of multiplication, the rules of exponents, because it's all one term. There's no addition or subtraction signs in between. Okay, so here's the rules. Let's see, y divided by y 4th, we subtract the exponents. Y has an imaginary first, so that gives us y divided by y 4th, that gives us y to the negative 3rd. So that gives us, let's see, 4x, and then we have y to the negative 3rd on top, over 4 times x negative 2 to negative 2. Okay, let's try the x's then. So so x has imaginary first power, and so 1 we have, let's see, we write that as 1 up here. We did 1 minus 4 up here, so y to the 1 minus 4. Down here we're going to do x to the 1 minus a negative 2. Okay, we're going to be careful about that. You don't want to just make it just 1 minus 2. This is 1 minus a negative 2. We're subtracting a negative, which means we have to add them. So this becomes a 1 plus 2. So that gives us x to the 3rd. So, cool. So that means, that this is 4 x to the 3rd, y to the negative 3rd, over 4. Interesting thing here, we can cancel out these 4's. These 4's can just cancel out because there's one on top, one on the bottom. We can just cancel them. And so we get left with x to the 3rd, y to the negative 3rd. And so we want to get rid of that. So that's really simple now. That's really, really close. And that's about as simple as it can go. We just have a negative exponent. We want to get rid of that negative exponent because that's no good. You probably could have seen it earlier and tried to get rid of it earlier. And if you did, great, perfect. We're left with x to the 3rd, y to the negative 3rd. And let's see, that becomes x to the 3rd divided by y to the 3rd, and that's our answer. And I want you to be careful. This one is kind of tricky because if you didn't do the y side correctly, you've gotten y to the 1 minus 4, and you might have accidentally put y to the negative 3rd at the bottom of the fraction. But no. Whenever you do that division, the answer always goes in the top side of the fraction. If that is confusing to you, or if that seems kind of irrelevant, if that's confusing to you and you are having problems with that, let me know. If that's still confusing anyway. But if that sounds really irrelevant, or that sounds just like offhand and weird, then don't worry about it. You probably didn't have to deal with it. Okay, next problem. We're getting pretty close to the end here. There's only 2 problems left in our video. We got 2x to the 3rd, y to the 3rd, times 2x to the negative 2, y to the third to the fourth. That is not a fun problem, is it? Well, let's work with what we know. If you remember from PEMDAS, all right, I really gotta stop being so fast. I'm trying to be so fast because I'm just not. We've got 4 copies of. Well, we're gonna deal with that parentheses first, and that parentheses, the thing that's happening with that parentheses, the thing that's closest to it, is that 4. We have 4th power, so we're gonna take care of that as soon as possible. So let's see, we'll take care of, we'll leave the 2x3 y3, or x to the third y to the third, x cubed y cubed, however you want to say it, on the left side. Maybe we even keep that multiplication sign as well. But we need to get rid of that 4th. And a few problems ago, we said we could do this by doing one thing. We could say 2x negative 2 y3, and we could do that 4 times negative 2 y3, 2x negative 2 y3, 2x negative 2, negative 2 y3. You can see that will take a long time to actually do. It takes some time to actually get that all done. But you might remember from the instructions from the very beginning of this video that there's a kind of a shortcut we can do instead of doing this over and over and over and over again and then multiplying all this together and putting it all together. This 4 can go into, we can multiply every bit by the 4s. This gets multiplied by 4, that gets multiplied by 4, and that gets multiplied by 4. Every single little bit inside of this parentheses, everything that's being multiplied together gets also multiplied, gets also raised to that 4th power. So here's what that means. Instead of doing all this junk down here, this takes forever. That's going to be hard as all get out. Well, not hard. It'll just take a long, long time. Let's do this instead. We have 2 to the 4th power. And be careful. Remember, we have to do this to the 2 as well. We can't forget 2. Even though the 2 is next to the x, everything inside here gets that 4. Because everything is getting copied 4 times with multiplication. Everywhere there's an imaginary multiplication sign, we have to put that exponent to the 4. So 2 times exponent to the 4. And then x to the negative 2 to the 4, and then times y to the third to the 4. Okay, let's see. So that reduces it down significantly. We're going to go ahead and do 2 to the. We'll just do that other rule of multiplication. We'll just actually incorporate those in. So we're gonna write 2x cubed y cubed. Here's what I mean. We're gonna look at these and evaluate each of these individually. So 2 to the 4th. What is 2 to the 4th? Well, let's see. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the 4th is 16. So okay, that's 16. And then let's see. X to the negative 2 to the 4th. We're just gonna multiply those exponents. Remember, that's stage 3. That's stage 3 of the instructions. Stage 3 is when they're together. You just multiply the exponents. So that's what we're going to do here. All the way back down here, we're going to multiply these exponents. There we go. So x to the negative 2 to the 4, that gives us x to the negative 8. And then over here, we get y to the 3, y cubed to the 4. Or to the, yeah, and that gives us y to the 4 times 3, or y to the 12. All right, we are making good progress here. Good progress. Now we can combine these together. We've gotten rid of all the parentheses, so we can just bring things together as well as we can. So we've got 2 times x cubed times y cubed times 16 times x to the 8th times y squared, or sorry, y times y to the 12th. Let's bring this together. We get, if I reorder this in a way it's a little more helpful, we get 2 times 16 times x cubed times x to the negative 8 times y cubed times x to the 12th. Okay, so 2 times 16, that's 32. 32. And then x to the third times x to the negative 8. That's, let's see, 3 minus 8. I have $3, and I lose, and now I get a ticket that says I owe someone $8. So I give him my $3, and that means I now still owe him $5. So I have negative $5. Yeah, so I get x to the negative 5. Okay, and then we do, let's see, y cubed times, oh, I say that ain't x12. I'm sorry, that's not an x, that's a y. y cubed and y12. We're going to multiply those together and add the exponents. 3 plus 12 is 15. So we get y to the 15. Great. And so let's see, that's almost done. That's almost as far as we can go. Let's get rid of those multiplication signs because it's kind of in the way. We get 32 x to the negative 5th, y to the 15th. Remember, because that just means when all the numbers are clumped together like that, just means there's imaginary multiplication signs between them. And let's see, that negative 5, let's see, we want to get rid of that negative 5, so we'll bring it to the bottom of the fraction and then put that 5, we'll make that 5 positive. Here's what I mean. We'll do 32 times y to the 15th, and we'll bring the x to the 5th to the bottom and make it positive. And let's see, there's no more negatives. Everything seems to be as simple as it can be. There's only one of each letter. Let's see, and it looks like that's about as good as we can get. So that'll have to be our answer. 32y to the 15th over x to the 5th. All right, last problem. And that looks nasty as all get out. Oh my. Okay, let's see a way of moving forward with this that's not as disgusting as what this looks like. Let's start with that again. Let's look at PEMDAS. We want to start with those parentheses, and we'll start with the biggest parentheses because that looks like the baddest. The biggest, baddest parentheses, and we'll work our way in. You could also work from the inside and work your way out. It doesn't really matter what you do. You can do what you want as long as you are following them, as long as you're not breaking any math rules. And let's see. So you could work from you can work from the outside and work out. We can work from the inside parentheses and go out, or you can work from the outside parentheses and go in. I'm gonna work from the outside parentheses because I think I like that more. So let's do that. So you get x to the negative 1 to the negative 3 to negative 3. So this negative 3 on the far outside, I can bring that in, and by multiplying, by bringing it into each of the terms, not the terms, but each of the things being multiplied or divided. So that negative 3 can go to both the negative 3 and the 4. And I'm raising a power to a power, so I multiply. So we get x to the negative first. It's really hairy. I know this looks really tough, but think about it this way. We're just trying to do the most basic thing at a time. And the first basic thing we can do is get rid of that negative 3 at the very, very far outside. We say, okay, I know what that is. That's x. Yeah, we can bring that in and make that x to the negative 3 times negative 3, or x to the 9th. Okay. And then we're going to take the negative 3 and bring it down to the 4. And we'll have 2x to the 3 to the 4. That's negative 12. 4 times negative 3 is negative 12. If that doesn't make sense, I'm gonna show another way of doing the same problem as well. That might make a little more sense to you. Maybe a little more intuitive. And then from here, let's see. I want to get rid of that negative 12. I guess. So I'm gonna bring that up, and So we'll do this. We'll bring the whole thing in parentheses up. We'll do x to the negative first to the 9th, and we'll multiply that by 2x to the 3rd to the 12th. Yep, so we brought it up and we changed the sign. That's what we did here. And then we're going to bring it, and then let's do with the other parentheses. The 9 on the x to the negative first, so it'd be x to the negative 9, and then 2x to the 3rd. We're going to bring that 12 into both terms, to the x to the 3rd and to the 2. So we'll bring both there, so that gives us 2 to the 12th power times x to the 3rd times 12. That's the 36th power. Okay, so we'll kind of reduce from there. So 2 to the 12th power times x to the negative 9, 9 times x to the 36. I see that 9 and 36 can combine to be 25. So that gives us 2 to the 12th times x to the 25th. No, is that 25th? No, that's 27th. Excuse me. 36 minus 9 is 27. 27. So x is 27th. Now, okay, what is 2 to the 12th power? Ooh, that's one we can do with a calculator, or we can just do it in our head. Let's see. Let's count it. So 1. Let's see. Our first power is 2. Second power. So 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth power is, let's see, 32, 6 is 64, seventh is 128, eighth power is 2, let's see, it's 256, and this is computer lingo if you're interested. These are the numbers that computers use all the time. So 512, and yeah, that's 50, 55, 12, and then 10 would be 1024, 11 would be 2048, 2048, that sounds like familiar, doesn't it? And then 12 is 4,000, let's see, 4,096. That'd be the answer. So 4,096. So we got 4,096 times x to the 27th, and that's our answer. You can block out that time in the middle if you want to, and that's our answer. And cool. So that's all the ways of doing that. If you want to find a different way of doing the same problem, let's see if I can find a different way of doing that same problem. Am I able to copy this? Yes, I can. I'm going to copy this and bring it right down over here and re-paste it. We're going to paste it back in. Okay, we're going to do the same problem again, and we're going to go a different approach. We're going to go from the inside out, because this might be a little less confusing for some people. Okay, so we'll start with x to the negative. We'll start from the inside parentheses, and we'll work our way out from there. So x to the negative 1 to negative 3. I don't know what this huge mess is, but I know what that is. X to negative 1 to negative 3. I can solve that by multiplying the exponents. So that gives me at the top x to the fourth. Sorry, not x to the fourth. Excuse me. It's x negative 1 times negative 3 is just 3 at the top, and then 2x to the fourth. I can bring that 4 in to both the terms, and we get 2 to the fourth times, let's see, x 3 times 4 would be 12 times x to the 12th, and then all of that is still to the negative third power. Now that I've done that, and we can reduce that down a little bit. So 3 and 12, x to the third and x to the 12th, that becomes x to the, let's see, that reduces down to 3 minus 12 is x to the negative 9. So that gives us x to the negative 9. Oops, not x minus 9. X to the negative 9 over 2 to the fourth. All that to the negative third power. And finally, we can take that negative third power and bring it in. So that gives us, let's see, that would give us, let's see, negative 2 to the negative 9, the 3 to the x. This negative 3 goes to the x, to the 9, and to the 2 to the fourth. So that gives us, let's see, negative 3 times negative 9 equals x and is to the 27th over 2 to the fourth, and 2 to the 4, let's see, 2 to the fourth to the negative third. That'd be, 2 to the fourth to the negative third. That is the same thing as saying 2 to the 4 times 3, and which gives us 2 to the negative 12. So that's the same thing as saying 2 to the negative 12 to the negative 12. I don't like that negative though, so I'm going to bring it up. So we'll say x to the 27 on the top, and then we're going to bring that negative up and change it to positive. So it'll be times 2 to the 12th. Okay, and then we know what 2 to the 12th was from when we calculated earlier. That's 4096. So x to the 27 times 4096, and then kind of move it over. So 4096 times x to the 27th, or 4096 x 27, and that is still our answer. Great. So a lot of things going on. If you're still confused about these problems, if you're into a problem that's like really, really heavy for you and you don't know what to do, just feel free to send me an email or with a screenshot of what's going on. I'll try to respond as soon as I can. If you want to set up a Zoom meeting so you can work through some problems together, I'm happy to do that. But yeah, man, I really hope you really get a lot out of this and really conquer this really disgusting thing. That is something that seems really disgusting, exponents. But I think when you really get into it, when you really get it, when it clicks, you can kind of see the beauty behind it, and see how God is doing great things through it. So anyway, I hope you enjoyed this video. I hope this finds you helpful. And again, let me know if you have any help. I'm here to help you as ever I can. So thanks for listening. Thanks for letting me get on all these tangents, and thanks for being here to learn. I love teaching you guys.